Today's lecture introduces the concept of radio interferometry. Radio interferometry is a technique for combining the signals from multiple radio telescopes into a single large synthesis telescope with much higher resolving power. First, let us consider the limits of single-dish telescopes. A typical radio dish looks like this. This is one dish of the Meerkat radio telescope, 13.5 meters in diameter, or perhaps like this. This is a 25-meter dish of the Hart-Beesthawk Radio Observatory. As was discussed in the lecture on single-dish telescopes, the size of the dish is directly proportional to its resolution. So, for example, given that we have a 25-meter dish here, and let's say we're observing at the famous wavelength of lambda 21 centimeters, the resolution of such a dish is only about half of a degree, or this is actually the size of the full moon. This is just about enough to tell whether it's made of cheese or not. Remember that ground-based optical telescopes can achieve resolutions measured in arc seconds. The problem radio astronomers have is that our wavelengths are up to 1 million times longer than the wavelengths in optical astronomy. So, what to do? So, the obvious solution is to build bigger dishes, right? Such as this 300-foot Green Bank telescope behind me. But this is very hard and very expensive engineering, and sometimes things even fall down. The biggest movable dishes we have in operation today are all in the 100-meter class. Anything larger than that is simply not practical without some help from Mother Nature. For example, the 300-meter Arecibo telescope behind me uses natural topography, a sinkhole in karst mountains in Puerto Rico, as part of its design. The dish is fixed to the ground, so it looks straight up, but we can steer where it effectively points in a limited sort of way by moving the receiver, which is mounted on cables here, along the focal plane. The recently completed 500-meter aperture spherical telescope, or FAST, in China, uses the same idea. This is absolutely the biggest dish we've managed to build, and still, the angular resolution is nowhere near close to that of optical telescopes. So, what can we do to get higher resolution? Well, a technique called aperture synthesis interferometry allows us to combine the signals from an array of many small telescopes, and small means cheaper, more robust, into a single synthetic aperture that has the resolution corresponding to the distance between the telescopes, what we call the baseline length. And this distance we can actually make very large. A technique called very long baseline interferometry can connect together dishes across the Earth, giving us continental-sized baselines of thousands of kilometers. In fact, we have even launched small dishes into space, giving us even longer baselines. Interferometry has given radio astronomers access to absolutely fantastic angular resolution. In fact, a very ambitious project called the Event Horizon Telescope aims to use this technique to image what is called the shadow of the black hole at the center of our galaxy. So how does all this work? Let's step back in time a little bit, back to 1803. That is when this gentleman, Sir Thomas Young, performed what is arguably the first interferometric experiment, the famous double-slit experiment, which should be familiar to everyone from basic physics. Behind me is his original engraving that he used to illustrate his experiment. Now, Thomas Young wasn't thinking about radio interferometry at all. Instead, he wanted to demonstrate the wave-like nature of light. At the time, this was still a controversial idea. Remember that Isaac Newton proposed the corpuscular theory of light. By 1803, many scientists were beginning to suspect that light was actually a wave. So Thomas Young devised an experiment to demonstrate this. And here's how it worked. You have a screen here at S1, and there's a pinhole providing a source of light. Thomas Young actually used sunlight. He didn't have electricity yet. The light illuminates a second screen, S2, with two parallel slits. And then this is projected onto a screen on the back here. Now, because light is a wave, each slit here can be thought of as a source of waves, and these waves interfere. Depending on the relative distance traveled, at some points the waves interfere constructively, two peaks come together, and at some points destructively, a peak cancels out a trowel. This results in a pattern of dark and light bands on the screen back here, which we call a fringe pattern. Now let's look at some of the mathematics behind this. Light is an electromagnetic wave, and at any point in time and space we can describe it by a complex number. so a quantity with an amplitude and a complex phase. So we say it's an EM wave. It has an amplitude and it has a complex phase. Actually, it's two complex numbers if we consider polarization as well, but for simplicity here we don't. Now, when we measure light with our eyes, for instance, or with a photographic plate or with a digital camera, you don't actually directly measure the electromagnetic field. Rather, you're measuring its brightness or intensity, which is essentially an average of the field over time. And we can write it like this. Brightness, B, is the average over time of the amplitude of the field squared. The angle brackets denote averaging over time. So we write it like this, E times E its own conjugate, which of course in this case is just equal to A amplitude squared. Now, where does the wave-like nature enter into it? To keep things simple, let's look at a monochromatic light source here. And then we have the field propagating along two different paths. Let's say E1 here and E2 here. And so the field arriving from this direction is E1 and the field arriving from this direction is E2. Now let's say there is a path length difference in the distance traveled along the two paths. In this case, the phases of the two fields received from E1 and E2 are going to be related, and they're going to be related like this. So if E1 is an amplitude times a complex phase, then E2 will be an amplitude times a complex phase minus phase 0. And this phase 0 difference will be given by 2p tau naught over lambda. This is what we call the phase delay. Now, the field actually registered at this point on the screen, E, is a superposition of the two fields. E is simply E1 plus E2. So let's work out what the brightness is. Brightness will be the average of E1 plus E2 times E1 plus E2 conjugate. So writing this out, we get E1 squared plus E2 squared plus E1 E2 conjugate plus E2 E1 conjugate. And that is equal simply to one amplitude squared, other amplitude squared, and then these two terms are simply equal to 2A1 A2 cosine of phi naught. So notice that none of these quantities actually depend on time anymore. So we can drop the averaging operator and write it like this. Also notice that these two things are constant pretty much. Doesn't matter where you are on the screen, the amplitudes are not going to change. But this, what is called the interfering term depends on phi naught, which is the phase difference, which depends on the path length difference, tau naught, and that depends on where we are on the screen. So as we move around on the screen, phi naught changes, so the interfering term changes, and that's what produces the fringes. Another thing which you can directly see from this is that the frequency of the pattern is determined by the spacing of the slits. If we move the slits further apart, the path length difference between these two path lengths increases, so the fringes, the spacing of the fringes, becomes finer. Now, as a mental experiment, let's reverse this picture. We know that physical laws have symmetry, so we can just flip the direction of propagation around. So imagine now that the screen is the sky, and that your eye is over here, so the waves are traveling this way from the sky through the two slits, and then they're gathered by your eye. Now, what is the physical meaning of the fringe pattern then? Well, turns out the fringe pattern becomes a sensitivity pattern. Let me explain how. So imagine we've got a small monochromatic source of light, and we move it around the screen here. If you place it on a trough of the pattern, if you place a source of light here, would you see the source with your eye here? Turns out you wouldn't, because waves from a source here would combine destructively so you wouldn't see anything with your eye, even though the source is right there shining away. On the other hand, if you move your source and you put it on a peak here, on a wideband, then you're going to see the source perfectly well, because waves from the source are going to combine constructively, and your eye will detect them. So it turns out that this is exactly how a radio interferometer works. So you put two antennas, you put an antenna here, and you put an antenna here. You combine their signal electronically, and what you effectively do, you cast this fringe-like sensitivity pattern over the sky. So for comparison, an antenna itself also has a sensitivity pattern, right? An antenna sees a certain patch of sky, and the size of the patch is what we mean when we talk about the resolution of the antenna. So an antenna looking this way would be seeing a patch of sky like this, and on the sky, that patch would be, schematically speaking, something this big. And remember, the size of that patch, the resolution of the antenna, this distance here, is given by lambda over d, where d is the size of the antenna here. Now, over this sensitivity pattern of the antenna, we get the high resolution fringes, with their spacing, the spacing between the fringes here, determined by lambda over b, where b is the baseline, what we call the baseline, the distance between the two antennas. So notice what's happened here. Our resolution, our ability to localize a source for a single antenna is given by the primary beam. The source can be anywhere in the beam and you don't really know where it is. And that's determined by the dish size d. For an interferometer, we magically get this much finer localization given by the fringes of the pattern, and this is limited by baseline b, which is much longer than the dish size. And of course, it's much easier to build two antennas and set them a distance apart than it is to build one huge antenna of size b. One of the first radio interferometers actually managed to pull off this trick with just one antenna. This is what they called the sea cliff interferometer, first done in Australia shortly after the war. This was the antenna standing on a cliff, and look what happened. So you have the surface of the sea, and then you have a cliff, and on the cliff sits your antenna, and you're observing a source. They were actually observing the sun, so the radiation came from this direction. Let's say the sun over here. But then, because of the surface of the sea and because of radiation reflecting off the sea, there was a second direction by which radiation from the sun entered the antenna, and that was this direction here. So you have radiation from the same source traveling along two paths and then adding up in the antenna as it hit the receiver. Now, if you think about it, you'll realize that this is exactly the same as if it had like a second virtual antenna under the sea. I'll try to draw it for you. So imagine the signal continue, instead of reflecting, the signal continues to propagate. And it's exactly like having a mirror image of your antenna under the sea receiving this radiation. So effectively what you get in the end is an interferometer with a baseline of b, and this is the baseline, which is basically twice the height of the cliff. So this is very clever. You don't need two antennas to make an interferometer, you can just use one. And with this setup, they could already do some pretty cool science. So here are actual plots from their observations of the sun. The game here was to see whether they could localize the sources of radio bursts to visible sunspots. Now, it turns out sunspots were the source, but because the resolution of a single antenna is much larger, say it could be as big as this, with a single antenna then, you can't really tell where the signal is coming from. The signal could be coming from the whole disk of the sun, which they've drawn here. It could be coming from a part of the disk. It could be coming from a sunspot, etc., etc. But because they set up a sea cliff interferometer, they got a fringe pattern across. So the fringe pattern they actually illustrate with these lines here. And we can continue this. So there's a fringe pattern cast across the sky. And then, as the sun rises, as a function of time, you can see the sunspot here. It's climbing in and out the peaks and the troughs of the fringe pattern. And if you then record the detected intensity on a strip chart, they saw a signal like this. And that's basically the sunspot tracing out the fringes of the sensitivity pattern. And based on that, they could say, yes, now we're sure that it's actual sunspots that radiate the signal and not the entire sun. So now this actually illustrates a very important point for interferometry. Sunspots trace the fringes of the sensitivity pattern because they're small relative to the spacing of the fringe here. Now, would they have seen a fringe if the radio signal came from the entire disk of the sun? No, because you're receiving an integrated signal from the whole disk, but some of this disk is sitting in the positive fringes, some of this disk is sitting in the negative fringes, and as it moves, it's still positive, negative. So overall, the signal gets washed out. So this is very important. You can use an interferometer to measure the size of an object. An object must be small enough for a fringe pattern to appear. Otherwise, there's no fringe pattern. Now, going back to optical for a second, the very first use of interferometry in astronomy was for exactly this purpose. Here, you see the Michelson interferometer constructed at Mount Wilson Observatory. In 1921, Michelson, this famous gentleman here, and his colleague Pease used this to measure the angular size of Betelgeuse, a red giant star. This worked more like the double slit experiment again, except instead of slits, you have these adjustable mirrors which you can move apart. The baseline, the distance between the two arms on which the two mirrors sat, was adjustable out to 6 meters. Now, the longer the baseline, the higher the resolution. So they started with a baseline of 1 meter, fiddled a lot to get it working right, finally observed fringes from Betelgeuse. Then they carefully increased the baseline until, at about 3 meters, the fringes disappeared. From this, they could infer a size for Betelgeuse of about half an arc second. And in fact, the term visibility, which you will be hearing a lot later, actually comes from those early days of interferometry. It meant literally the visibility or the contrast ratio of the observed fringe pattern, which they observed by eye in the eyepiece. Now, getting back to radio, while the Australians were using cliffs, over in the UK, Martin Ryle's group at Cambridge built the first Michelson radio interferometer. It was called the Long Michelson. Long, in this case, meant just two antenna elements 440 meters apart. In many ways, this was the precursor of all modern radio interferometers. Schematically, a modern radio interferometer array is just a combination of many such long Michelsons, and most of the signal path is replaced by electronics, and these days it's mostly digital electronics. Each pair of antennas makes a single interferometer. For Meerkat, for example, where you have 64 antennas, you then have about 2,000 possible pair combinations between them, so you have about 2,000 Michelson interferometers operating simultaneously. Another important development made on the way was the multiplicative interferometer. All the interferometers we've seen so far, starting with the double slit experiment and the Michelson interferometer, have been additive. Additive because you form a fringe here by adding the signal from the two arms and then taking the average in time. Now, if you recall the math we did earlier, you'll see that the measured intensity consists of these four terms. Now, this one here and this one here is constant. It does not depend on the baseline. So all the interferometric information is actually in these two cross product terms. This is where the fringes ultimately come from. And in the radio regime, because we're dealing with long wavelengths, we have an important luxury. We're pretty much able to measure E1 and E2 directly. So our electronics are fast enough to actually measure that. And so in a modern radio interferometer, we don't even bother about these two signals because we can measure E1 and E2 directly and then basically multiply them in the big computer that's called the correlator. And that's a multiplicative interferometer. And this brings us to our final subject, imaging. Now, your traditional optical telescope, whether it was one of Galileo's first telescopes or whether it's the Hubble Space Telescope, is an imaging instrument. And what that means is electromagnetic radiation goes in, E's go in, and then an image of the sky comes out. And an image of the sky is lots of data. Every pixel is a data point. By contrast, early interferometers operated very differently. They were all pretty much one-off experiments. You rig up this incredibly complicated contraption, you fiddle around a lot to get it to work, and then radiation goes in, E's go in, and then one number comes out, your visibility. Just one data point. Now, what Martin Ryle and others quickly realized is that that single number is actually what's called the Fourier mode of the sky image. Or, one coefficient of a Fourier series, named after this famous mathematician here. If you measure enough of these so-called Fourier modes, then you can use Fourier transforms to reconstruct an image of the sky from all these numbers that you have measured. This technique, called aperture synthesis, eventually won Martin Ryle the Nobel Prize and transformed radio interferometers into true imaging instruments. As you'll learn over this course, a modern radio interferometer array can give you a true image of the sky at radio wavelengths. To get a more intuitive idea of how aperture synthesis works, let's do something very traditional for physicists. Let's do a thought experiment. So imagine we've managed to build a very large dish, say 100 kilometers across. A dish works like any other telescope. Radio waves come in here, they reflect off the dish surface, and they're gathered in the receiver at the focus. Now, as a first step, let's break up our imaginary dish into sections like this. We're just going to break it up here and here and here and here and here. Nothing changes, right? The waves are still collected in the same way. Now comes the first trick. We've broken the dish up into sections. Let's put a little receiver here next to each dish section. A little electronic receiver. Then here, instead of having the waves travel to the central receiver through free space, we replace this section by wires. So you have a receiver here, and you have cables which bring the information to the central receiver. And now it looks like this, right? Now you can imagine that in some way we still have the same system as before in terms of imaging performance. So the only thing that's changed is instead of having radio waves propagate through free space here, we've got the same signals, but now they're traveling over cable. As long as we build everything carefully, the result is going to be the same. But now, if you think about it, if this is cables, then do we really need to keep the sections up here in the air where it's kind of difficult and expensive to keep them mounted? Well, actually we don't. We can drop them all on the ground like this. So the difference is that now radio waves have to travel a bit longer to get to the individual dish sections. So we'll have to make our signal cables longer to kind of compensate for this. But you can imagine if we do everything exactly right, the end result is still the same. And that is the essence of aperture synthesis. We have many small dishes, many small antennas on the ground, which synthesize a large aperture dish. And I do this using a device called the correlator, which brings all the signals together, and some clever software called the imager, which basically does Fourier transforms. And for the final trick, let's remove some dishes. Here and here and here, then we have a sparser array, and it's cheaper to build. Because, as we'll see later, with some clever mathematics, we can almost make up for the absence of these dishes. Why does this work? Well, going back to the schematic of a single telescope, let's work out what the electromagnetic fields are. So let's say we have a coordinate system on the sky, which we'll call L and M. And then we have a coordinate system on the dish, which we call U and V. Now it turns out that if you want to work out what the electromagnetic field is on the surface of the dish, let's call it V as a function of U and V, you can work it out. It's a sum, an integration of fields arriving from every direction on the sky, from every LM direction. So we'll call it SLM. This is the sky signal, and it's multiplied by a complex phase term, which looks like this. And then it's integrated over all directions, dl and dm. And that's the field at a single point on the dish. Now the signal reflects off the dish, goes to our receiver, goes to our focal plane. So in the focal plane, let's say we have coordinates named x and y. Now, what is the electromagnetic field at the detector here? Let's call it I as a function of x, y, position on the detector. Well, now we have to take the contribution from every field on the surface of the dish. So we write it like this, V of U and V, times also a complex phase exponent. And then we have to integrate that over all the bits of the dish, so it's an integration over u and v. And these complex exponents, they simply correspond to the travel time of the signals. Remember the path length difference, the phase delay from the different bits of the dish to the receiver. Now these things here, you can basically recognize them as Fourier transforms. So basically, the field at the aperture is a Fourier transform of the sky, and the field at the detector is a Fourier transform of the aperture field. And those two Fourier transforms then give you an image of the sky back. Your eyes are actually the world's fastest computer for doing Fourier transforms. As you watch this video, there's two Fourier transforms happening all the time before the signal hits your retina. And this is true for any optical system. So the premise of aperture synthesis is actually very simple. We measure the field in the aperture plane, where it's a Fourier transform of the sky, and then we do the second Fourier transform in software, and that recovers the sky image for us. As you can see, we've replaced a large and impossibly expensive dish by an array of small, cheaper dishes, some cables, some hardware, and still we have the imaging performance similar to the original impossibly expensive large dish. And that, in a nutshell, is radio interferometry. Thanks for listening.